All right, let's get into it. Today, we're taking a journey from the stuff we can see to the stuff we can't, from simple everyday waves to the actual building blocks of energy itself. We're going to unravel the quantum nature of light.
I mean, really think about it. What do these things have in common? They seem totally different, right? But here's the thing. They're all fundamentally the same stuff, just wearing different disguises. By the time we're done here, you'll see exactly how they're all connected. Okay, let's dive in. So, to really understand light, to understand energy, we have to start with the most basic idea of all, the wave. It's the foundation for literally everything else we're going to talk about. So, what even is a wave? Well, picture this. You've got a long rope tied to a doorknob. If you flick your wrist, you see that ripple, that S shape, travel all the way down the rope. Now, the rope itself didn't fly across the room, right? But the energy from your flick did. That's a wave. It's just a way to move energy around.
Of course, not all waves are created equal. And to tell them apart, scientists look at a few key measurements that are kind of like a wave's unique fingerprint.
First up, you've got wavelength. That's just the distance from the top of one wave to the top of the next one. Easy enough. Then there's frequency, which is how many of those waves pass by a single spot every second. And finally, amplitude. That's just how tall the wave is. A taller wave, a bigger amplitude, means it's packing more energy. Okay, so we've got the basics of a wave down. Now here is where it gets really interesting, because that simple idea unlocks this huge invisible universe of energy that is all around us all the time. You know, it's pretty incredible when you think about it. All the colors we can see, the whole rainbow, that's just a tiny, tiny sliver of a much bigger picture. This giant family of waves is called the electromagnetic spectrum, or EM spectrum for short. And it is a vast family. I mean, it starts with these long, lazy radio waves that bring music to your car. Then you get microwaves that heat up your leftovers, the X-rays a doctor uses, all the way up to these incredibly powerful, high-energy gamma rays from deep space. They're all just different kinds of electromagnetic waves. Having trouble keeping that order straight? No worries. Here's a handy little trick to remember the spectrum, from lowest energy to highest. Just remember this sentence. Roger makes instruments, violins, ukuleles, xylophones, and guitars. And there you have it. Radio, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And just look at this table. The scale we're talking about here is just mind-boggling. A single radio wave can be as big as a building. And at the other end, a gamma ray's wavelength is smaller than the nucleus of a single atom. The range is just absolutely incredible. So for a long time, this wave model seemed perfect. It explained pretty much everything. But right around the turn of the 20th century, a German physicist named Max Planck stumbled onto a puzzle that was going to change physics forever. He asked this really out there question. What if energy doesn't flow smoothly, like water out of a faucet? What if it came in little individual packets? Like a faucet that could only drip, one single drop at a time. And through his work with glowing hot objects, Planck proved his crazy idea was right. Energy wasn't continuous after all. It was being spit out in these distinct, measurable chunks. And he gave these little packets of energy a name: quanta.
So a quantum is the absolute smallest unit of energy you can possibly have in any given situation. You can't have half a quantum, you can't have a quarter of a quantum. It's the bottom floor, the fundamental, indivisible piece of energy.
Great way to think about this. It's like a penny. In the US, a penny is the smallest amount of money you can have, right? You can't pay for something with half a cent. It just doesn't exist. Well, a quantum is basically the penny of the energy world. It's the minimum amount. Now, this was crucial. Planck didn't just come up with the idea, he figured out how to measure the energy of one of these little packets. His famous equation, E equals hv, shows that the energy of a quantum, that's E, is directly tied to its frequency, v. So, a higher frequency wave is just made of more energetic packets. Planck basically cracked open a door to a very strange new world. But the guy who really walked through it and flipped on all the lights was a young Albert Einstein, who used this quantum idea to figure out the true and very weird nature of light itself. So Einstein started looking at this weird mystery called the photoelectric effect. Scientists knew that if you shined a light on a piece of metal, sometimes electrons would pop out. But they couldn't figure out why it only worked with certain colors of light. Einstein's solution, using Planck's quantum idea, is actually what won him the Nobel Prize. Here's a really good way to get it. Imagine an electron is like a basketball you're holding onto super tight. Now, if someone comes up and gives it a little tap, that's like low-frequency light. Nothing's going to happen. But if someone gives it a hard, sharp shove, that's like high-frequency light. The ball gets knocked right out of your hands. It takes a certain minimum punch of energy to do the job. And this was Einstein's genius insight. He realized light itself must be made of those energetic shoves. He said a beam of light isn't a continuous wave, but actually a stream of tiny energy particles. And he called these particles of light photons. And here's where it all just clicks into place. When Einstein went to calculate the energy of one of his photons, he found it was described by the exact same equation Planck had used for his quanta of energy, E equals hv. So what's the deal here? What's the relationship? Well, think of it like this. Quantum is the general idea, the concept of a minimum packet of energy. A photon is just the specific name we give to a quantum of light energy. So, yeah, a photon is a quantum of light. They're the same thing. And these photons are wild. They have zero mass, zero charge, and they zip through a vacuum at the fastest speed possible in the universe, the speed of light. And every single type of electromagnetic energy, from radio waves to gamma rays, is made of these little guys. Which brings us to this amazing paradox, right at the heart of quantum mechanics. We started our journey talking about waves, but we ended up with particles. So which one is it? Is light a wave, or is it a particle? Well, the completely mind-bending answer is, it's both. Depending on how you measure it, light acts like one or the other. And wrapping your head around that wave-particle duality, well, that's your first big step into the strange and wonderful world of quantum physics.